A processor that runs at a higher clock speed is not automatically a better choice for controlling a car. A vehicle controller may need to measure several signals at precise moments, respond to an event immediately, update a motor output before a deadline, detect internal faults, and continue operating across major changes in temperature and supply voltage. Raw speed helps, but predictable control matters more. This is why automotive electronic control units commonly use microcontrollers. A central processing unit, or CPU, is the part that executes program instructions. A microcontroller, or MCU, contains one or more CPU cores together with memory and hardware peripherals on the same chip. The complete ECU contains the microcontroller plus the power supply, input circuits, communication transceivers, output drivers, connector, printed circuit board, and enclosure. These three terms must not be mixed together. The CPU is a processing core. The MCU is the integrated computing chip. The ECU is the complete electronic control assembly. At the center of the microcontroller, the CPU repeatedly fetches an instruction, decodes what it means, and executes the required operation. A clock coordinates this activity. A faster clock can permit more operations per second, but useful performance also depends on the processor architecture, memory access, peripheral design, software structure, and competition for shared resources. The program normally resides in non-volatile memory, such as embedded flash. Non-volatile means that the contents remain when electrical power is removed. Flash may contain startup code, application software, basic software, calibration data, and other configured content. Random access memory, or RAM, stores temporary information while the software is running. Sensor samples, counters, task stacks, communication buffers, and intermediate calculation results may be placed in RAM. When power is removed, ordinary RAM normally loses its contents. Some microcontrollers also provide separate data flash or other non-volatile areas for information that must survive power cycles. Memory layout is a deliberate engineering activity because program code, runtime data, task stacks, communication buffers, and retained information have different requirements. A microcontroller becomes especially valuable through its peripherals. A peripheral is a hardware unit that performs a specialized function without requiring the CPU to control every individual electrical transition. An analog-to-digital converter, or ADC, converts sensor voltages into numeric values. Digital input and output hardware reads switches or controls low-power logic signals. Timer units measure intervals, capture the exact time of an input edge, and generate periodic events. Compare units can change an output when a timer reaches a configured value. Pulse width modulation, or PWM hardware, produces precisely timed output pulses for motor control and power control applications. Communication controllers handle protocol-related work for interfaces such as CAN, LIN, Ethernet, SPI, or CENT, depending on the selected device. The physical transceiver may still be a separate component inside the ECU, as discussed earlier. Consider an electric power steering controller. A steering torque sensor reports how strongly the driver is turning the wheel. Other inputs may include steering position, motor current, and vehicle speed received from another controller. The microcontroller must collect those values, validate them, and calculate the required motor assistance. It must then update the power electronics that control the motor. This sequence repeats continuously. A timer may create a periodic event, perhaps once every millisecond in a conceptual teaching example. That event tells the software that the next control cycle is due. Sensor values are acquired, the control calculation runs, and new PWM values are prepared for the motor control hardware. The calculation must finish before the next required update. Completing the correct calculation after its deadline can still produce unacceptable system behavior. Real-time control therefore concerns predictable completion within defined timing constraints, not merely a high average processing speed. Microcontrollers use interrupts to react to important events. An interrupt service routine, or ISR, temporarily redirects the CPU. A timer expiry, completed ADC conversion, received communication frame, or detected hardware fault can generate an interrupt. Interrupt priorities help determine which event receives attention first. An urgent motor control event may need a higher priority than a routine background activity. Interrupt handlers should normally perform only the immediate work required by the design, because a long interrupt can delay other time-sensitive processing. Direct memory access, or DMA, provides another way to reduce CPU load. A DMA controller can transfer data between a peripheral and memory without making the CPU copy every individual value. For example, a sequence of ADC samples may be moved into a RAM buffer while the CPU performs a control calculation. The DMA may notify the software when the transfer is complete. Modern automotive microcontrollers can contain multiple processing cores. Separate cores may run different software partitions or share a complex workload. Multicore processing does not automatically make software faster. Engineers must manage shared memory, synchronization, communication between cores, and interference over common hardware resources. Lockstep is different from ordinary multicore processing. In a lockstep arrangement, two processing paths execute corresponding operations so their results can be compared. A disagreement can indicate a hardware fault. The second path is therefore primarily used for fault detection rather than as a freely available core for unrelated software. Additional hardware mechanisms may include error-correcting codes for memory, clock monitors, voltage monitors, watchdogs, built-in self-tests, memory protection units, and central fault collection logic. Their exact availability and use depend on the selected MCU and system design. The presence of safety mechanisms does not make the complete vehicle function safe by itself. Safety depends on system requirements, hardware architecture, software behavior, diagnostics, integration, and verification. The MCU provides mechanisms that engineers can use as part of a larger safety concept. Security has also become part of automotive MCU design. Some devices include protected key storage, cryptographic accelerators, secure boot support, and hardware security engines. Secure boot helps establish that authorized software is loaded before normal execution begins. These features still require a complete project security design and correct lifecycle management. Power consumption is another concern. An ECU should not unnecessarily drain the vehicle battery while the car is parked. Automotive microcontrollers may support run, sleep, standby, and other low-power modes. Selected timers, pins, or communication events may remain capable of waking the controller. Software must save the required state, enter the correct mode, and restore operation in a controlled sequence. Therefore, selecting an MCU involves more than choosing the highest clock frequency. Engineers consider processing load, worst-case execution time, flash and RAM capacity, peripheral types, number of channels, communication interfaces, pin count, package, temperature range, power modes,
code,
safety
examines
mechanisms,
automotive
security
embedded
features,
software,
and cost.
what it contains, how it is
AUTOSAR
structured,
provides a
and why
software
vehicle
structure
software
around
is
this
different
hardware.
from an ordinary
In
computer
AUTOSAR
application.
Classic, the microcontroller abstraction layer contains hardware-oriented drivers. Microcontroller drivers and I/O drivers provide configured access to MCU functions and peripherals, while higher software is separated from direct register manipulation.
The application should not need to know every register address of a particular microcontroller. Lower-level drivers handle hardware-specific details, while configured interfaces allow the rest of the software architecture to use the required services. When an interviewer asks what an automotive microcontroller does, avoid saying only that it is the brain of the ECU. Explain that it integrates processing cores, program and data memory, timers, converters, communication controllers, and supervision hardware. It executes the embedded software, reacts to events, exchanges data, and controls peripherals within timing, power, and reliability constraints. The hardware is now ready, but it still cannot control the vehicle without carefully organized instructions. The next lesson moves from the chip